Hey everyone, today we are going to start looking at some more advanced things. We're going to specifically be looking at LoRA, or low rank adaptation. So LoRA has very quickly become one of the most popular methods of fine-tuning, especially really big language models, but technically you can apply LoRA to literally anything. So what we're going to do today is build LoRA completely from scratch. Now, just as a caveat, if you are actually needing to use LoRA and you're most likely using a Huggingface model, then go ahead and use PEFT. PEFT is an incredible package. It's already basically built in to all the different language models or models in general in Huggingface. And so you can go ahead and just kind of follow the instructions and apply LoRA to their different models. But the question is, why do we use LoRA? What is LoRA? And what are the benefits that we get from LoRA? So those are the questions that I want to answer today, and we'll kind of see how this works out. So let's first go ahead and just explore the intuition of LoRA, and then we'll start implementing it piece by piece, and hopefully it'll make sense by the end. So like I mentioned, LoRA is a technique to fine-tune models, and specifically it's to be able to fine-tune models with limited resources. So let's kind of explore what are the methods we typically use to fine-tune models. So in standard fine-tuning, what you'll do is, let's say you have some model, right? You have this model here, and let's say this is a model like RoBERTa. So if you've seen one of my previous videos, you've probably understand what RoBERTa is, but this is a model that's been trained with the mass language modeling technique. But typically, these models that are pre-trained on mass language modeling or in causal language modeling for models like GPT, Llama, stuff like that, the task that it was pre-trained on is kind of useless to us because effectively you either have a really fancy looking fill-in-the-blank model, or you have an autocomplete model. That's effectively what these models are trained to do. So what we typically want to do is take an existing model and fine-tune it to do something new and something that we care about. So what's something that we typically care about? We can use sentiment classification because I think that's the example that we'll be doing later. We can do sentiment classification. So to do sentiment classification, we take our base model that's been trained to do something and we add a prediction head, right? So it's typically just a linear layer or a couple linear layers. And this head will basically predict, is it happy or is it sad, right? That's your sentiment classification, and you're going to pass some text into the model, right? Or text embeddings into the model. So there we go. That's our typical setup. We're going to be fine-tuning. And there's two ways we can actually choose to fine-tune this model. Either one, we fine-tune everything, right? So we'll fine-tune both the head and the model backbone. So we'd be fine-tuning the weights of RoBERTa as well. So that's fair game. The second method is we just fine-tune the head and we freeze the model. So we won't be updating any of the weights inside this model. So these are kind of the two typical ways that that you see fine-tuning happening. But as long as you have sufficient data, of course, you typically get better results when you fine-tune the entire model along with the head. So fine-tuning more of the model typically leads to better results is the name of the game here. And so what's the problem with fine-tuning the entire model? When we're working with kind of these research grade transformer models that have, or it can be any model, but we're doing transformers as an example right now. We're doing these transformer models that typically have 12 transformer blocks with 12 heads and an embedding dim of 768, like the typical shape we see these transformer models in. We are dealing with anywhere from about 90 million to about 150 million-ish parameters. So this is kind of the range of model that we're working with, right? And so this is, fine, but this is actually quite a number of parameters to train, which means you still need some reasonable amount of compute resource to do it. You'll need multiple GPUs and all that sort of stuff to get a reasonable batch size, right? So that's the problem. We have all these parameters to train. So what LoRA does is ask the question, can we train with less parameters? And it does it in a really cool way, actually. So we'll take a look at that in a bit. But if we kind of add all these together, this is what we're dealing with. So on our GPU, right, on our GPU, we have to train all of these parameters and the intermediate activations, and we'll kind of talk about that in a bit. So we have quite a bit of GPU memory necessary to pull this off. So let's think if there's a better way of doing it. And we're going to go through effectively the thought process that would get you to something like LoRA. So step one is this. Let's just take one single weight layer. So I know there's lots of them in a neural network, but let's just take one of them as an example. So what we have, right? Well, how do we typically do this? We have a weight layer, look kind of like this, right? These are my weights. And typically in a neural network, right, you'll have maybe 768 inputs and 768 outputs, right? So this is a typical, let's say we take the query layer in a standard transformer, you'll have a 768 embedding input, 768 output. Very typical model. And so we'll have some X, right, go into this weight layer and it'll produce some output and we're good to go. And in traditional fine-tuning, assuming we're actually fine-tuning this layer, in traditional fine-tuning, you would effectively train this model and you'll create a brand new W prime, right? A W prime that has been optimized. So you started with W and you continued fine-tuning the model and you end up with some brand new W prime that is better at doing the task that you care about. So W prime is again a 768 input. Nothing changed, right? It's the same weight matrix, just the weights have now been updated to be able to actually do your new task. So there we go. That's basically the change. And so this is the way you should now consider the decomposition. So let's kind of we'll get to the low part of LoRA in a bit, the low rank part of it. For now, let's just start with the basics. W prime is new weights. W is my original weights. And so can we not write it actually this way? What if we said that W prime, let's write it on this side now, W prime. What if we said that W prime is equal to the original weights W, so what we started with, plus the delta W. And this is effectively the change. So when we fine-tune the model, we got brand new weights, W prime. But W prime came from W. So what we can say is that really the new weights is the original weights plus whatever we changed on those weights, right? So whatever we changed. And again, this delta W would just be another 768 input, 768 output weight matrix, just like that. And so now the question becomes this. Instead of passing, so this is what we want, right? We take X, we pass it to W prime, and we get some output, and we're done. But instead of doing that, what we can actually do, we can leave this 768 there. We can take an X, we can pass it to our original W, and we can pass it to our delta W, the change. And for now, assume we just have delta W. We haven't gotten there yet, but we pass these two things in. We produce an output from both of them, right? Some output. And then we can take these outputs and add them together. And this operation of me passing X to W, passing X to delta W, adding it together is exactly the same as just me passing X to my updated W. So these are both identical operations. And again, I can prove this to you because me passing X to W prime is just doing X times W prime is equal to X times W plus X times delta W, right? That's the setup. And that's the same as just doing X times W plus delta W. And I already know that W prime is the same as W plus delta W because that's how we defined it, right? So we can kind of keep that as a note up here. Our W prime is defined, right? Defined as W plus delta W. And so the question now becomes, well, instead of training W, what if I freeze? So again, W are my pre-trained weights, what I started with. What if I go ahead and freeze it? So I'm just going to use blue to freeze it, right? So we go ahead and freeze W. So this is no longer trainable. What we'll do is just train delta W, which means what we're learning really, and I mean, it's essentially the same thing, but what we're really learning is the difference between the original weights and the new weights, right? So what we're learning is delta W, whatever the perturbation was to the original weights to get here. It's still the same thing, right? It's still the same idea. It's just we're adding things. We're just adding this on now. So again, we're freezing W, but we are training delta W. So does this do anything? Well, actually, so far it doesn't do anything for us. It doesn't help us in any meaningful way because what did we start with? W, which was the original weight parameter, had 768, let's do it in the same color, 768 squared number of parameters in this layer. Delta W is still a 768 input, 768 output. So it's still 768 squared parameters. So nothing changed. There was no, like, doing this, if we had just done it this way, doesn't add any meaningful, there's no value here. There's nothing to do here. And so this is where the low rank part of this comes from. The authors of the LoRA paper basically asked the question, what if we can learn delta W in a lower dimension? Like, we don't need to learn this full delta W matrix. We can learn a compressed representation and add that in instead. So what they basically said is, instead of just learning delta W, right? Let's erase this. Actually, we can leave the that one because it's still 768 squared. What if we break it up like this? Instead of doing that, we're still going to have 768 input. That cannot change. We're going to learn something like this, and we're going to call this matrix A. And actually, let's make it more like a trapezoid so it's clear. There we go. This is matrix A, and we're going to go from 768 and compress down to some hyperparameter called the rank. So the rank of the, or just R, so rank. So we're going to compress from 768 down to R. And then what we're going to do is go from R back up to 768. Now, in all practical terms, this is the same. So for example, we had a 768 input, 768 output in this one weight matrix, and that produced an output of size 768, right? Out if the input is 768 output, so there we go, 768. This new one, and this is called B. In this new one, we're going to take X, we're going to give it to something that's 768 input, compress down to R, but then decompress back up to 768. And so this is also 768, and so this addition is still valid. It's just we're doing it through this compressed representation. And the reason it's called a rank is because if you know the rank of a it just comes from some linear algebra terms about what the rank of a matrix is, the number of linearly dependent columns, that sort of stuff. But they're basically saying the claim here is that delta W, this whole thing now, is now delta W. It's encoding the same delta W, but without doing a full 768 to 768 projection. We're doing 768 to a smaller rank and then rank to 768. And this is going to be our W. Now, so delta W in this case is going to be A, B, right? A times B, because A is 768 by R, right? That's this matrix going from 768 to R. And then B is going from R to 768. So we get the same 768 by 768 matrix at the very end, right? We get the same 768 by 768 matrix at the very end, except we're going through this lower rank. And this should kind of make you think of PCA or autoencoders and things like that. It's the same idea, right? Instead of learning it at the high dimension representation, let's learn what we want to learn at some lower dimensional representation. But that's the key idea. We're representing delta W as A times B instead of just one big delta W matrix. Now, this is only useful if, R is sufficiently smaller. So we're going to do double less, right? Is sufficiently smaller than our 768. Because if R is very close, if let's say we pick 760 for R, then there's really not, again, much of a gain that we're making here. So it's kind of pointless. So instead, let's say we pick an R rank as 4, right? So that means we're going to go from 768 to 4. So that means A has 768 times 4 parameters in it, right? That's our weight matrix. And then B is going to be 4 input times 768. And this number here, I don't know what it is off the top of my head, but whatever it is significantly smaller than 768 squared, the number of parameters that we had started with. And this is the key idea of LoRA. Instead of learning some big delta W matrix, right, which would have been the perturbation, right? That would have been the perturbation we added to W to get our effective W prime, because that's our goal. Instead of learning delta W at the full dimensional representation, let's learn some compressed version of it. And this will reduce, again, remember, W is frozen. So in our big model, all the weights that we convert to LoRA, and we'll see what that looks like in a bit, all the weights, we leave them alone. We don't even touch them. We don't train them. We don't need to compute gradients for them. So that's a huge cost savings in terms of the memory use for our model. On the other hand, we do need to train A and B. A and B are now trainable parameters, but A and B, the total number of parameters in A and B together, is so much smaller than 768, so we're getting some memory savings there. And again, this is just the main idea behind LoRA, and so we'll come back to this picture. We'll kind of reference this as we go. Actually, no, there is one more thing we do need to talk about. We don't just directly add. There is a little bit more that goes into it. What we do is we say our output, our final output, is going to be, and let's not do it in red so it's clear, let's do orange. Our final output is going to be, we're going to pass x to w, right? So it's going to be just xw plus, we're going to have some scaling factor here, times x AB, right? So x times A times B will give me basically my x delta W, like the fake x delta W, the low dimensional representation of x delta W. So this is the same as doing x delta W, technically, right? Some approximation of it. And then this is a scaling factor. And typically for the scaling factor, we use alpha over R. So alpha is a hyperparameter, and R is the rank that you pick. Okay, so that's the key idea. Alpha is some hyperparameter that we have, and R is the rank that we pick. And so how do we pick out, or not really how do we, but what is alpha? Alpha is basically you can think about it like a strength parameter. W is frozen. And so W prime, how much perturbation, remember, we're basically doing W plus delta W, but instead of doing W plus delta W, we'll be doing W plus alpha over R delta W, right? So, and delta W is again parameterized by AB. But either way, this is effectively what we're doing. And so if alpha is a very small number, that means whatever perturbation our model learns, whatever the A and B learns for delta W, it doesn't really matter because we'll be only able to change W a little bit, right? We can only perturb W by whatever alpha is. So if alpha is 0, we can't change W at all. If alpha is a very small number, we can do small changes to W. If alpha is very large, then we can do large changes to W. So it's basically your strength factor, or however you want to think about it. It's just how much of my delta W, how much of W am I willing to allow to change? How much tolerance will I allow to change? And we typically scale it by R. So we divide by R, and this makes sure that as your rank gets bigger and bigger, this matrix here can learn more interesting and complicated relationships, right? Because there's more learnable parameters here as your rank gets larger. So as your rank gets larger, we want to make sure we scale it down by R, as just basically inversely weighting it. As rank gets larger, we want to allow for less perturbation to the original W, just for that reason. Now, this is fine. This is the original implementation of LoRa, but then another paper came out called LoRA, where they saw that this paradigm actually slightly unstable for large R values. So you can take a look at it. For large R values, they were able to show that doing the square root of R instead led to better results for larger R values. So you can, again, go take a look at that paper. It's pretty interesting. But I'm not going to go into too much depth into too many different things, or this video will end up taking just forever. So LoRA, we scale by square root of R. Regular LoRa, we scale by R. And LoRA, I think, is basically used by default because it just has empirically better results. So that's what we're going to be using. So again, we'll come back. We'll refer to this figure as we're building our model. But let's go ahead, and I think the best way to understand this is just to build it. What we're going to be doing today is building 3 different LoRa layers. The first one is going to be a LoRALinear layer, then we'll have a LoRAEmbedding layer, and then we will have a LoRa convolution conv2D layer. So these are typical layers that you'll be using in all of your different neural networks. And again, the purpose of what we're about to write here is going to be LoRa that can be applied to any model, right? So it's not kind of restricted to Huggingfaces or whatever. You can just apply it to your own. And then we will have to write a class basically that can convert an existing model to a LoRa model. That'll make more sense once we kind of get there. And then I won't be writing a training script in this video because it'll just go on forever. I've written plenty of training scripts. So we're going to just take we're going to fine tune RoBERTa to just do some simple classification tests, so nothing crazy. So either way, let's go ahead and get started. So we need math, import torch.nn as nn. We're going to do import torch.nn.functional as f. We're going to do from data classes import data class, just like that. We need from, and these are more for organization purposes. We're going to do from typing import optional, literal, and union. So we'll see what those are. And then we needed the ability to save our model, and we'll talk about how we save models in just a bit, and weight merging. So we'll get there. But for now, we're going to do save file. So there we go. So these are, I think that basically covers all the imports we need. So the best way to start this is just by implementing, I think the linear layer kind of makes it very clear about exactly what's going on. So let's go ahead and do that. So what we're going to do is create a class. We're going to create a base layer, basically. LoRA layer base or whatever, right? LoRA layer base. And what we're going to do here is just define the things that will show up in every single LoRA layer, right? So just the common stuff. So we're going to do def init, self, and then we're going to define all the stuff that we care about. So what is the rank that we want? What is the alpha that we want? 8 and 8, whatever. I'm just picking random numbers here. We will have a dropout layer. So what's the dropout probability? And then use rs LoRA equals true by default. And again, this is a very minimal implementation, but it is powerful and it does work. Huggingface will have, or PEFT, I guess, will have even more options that you can use to configure your LoRA model, but this is kind of the main stuff that you would care about when doing it. So we're doing it here. And let's just save all of this stuff as attributes that we can access later. LoRA alpha, LoRA dropout is LoRA dropout, and self dot use rs LoRA is rs, or use rs LoRA. There we go. And then let's go ahead and also define our self.LoRA. Actually, LoRA dropout should be a dropout layer. So let's do this right here. And then dropout. And this is going to be a dropout with the LoRA dropout scaling if LoRA dropout is greater than 0, right? So if we set it 0. Otherwise, if we don't want any dropout, then we can just do lambda x, right? So we'll just return back everything. This is just we could have also used nn.identity. It just won't show up in the model then. So there we go. And like I mentioned, we have our scaling factor, right? So alpha over r or alpha over square root of r if we're using rs LoRA. So we can do self.scaling. It's going to be self.LoRA alpha divided by self.rank to the power 0.5. That's the square root if we're using rs LoRA. Otherwise, it's just going to be self.LoRA divided by self.rank, and that's it. And so, no forward. We also need the ability to load a pre-trained weights. And so this will make more sense why we have it later. But for now, we're just going to write it. Load pre-trained weights, self state dict. So basically for a specific layer, right, when let's say we create a brand new LoRALinear layer, but LoRALinear layer on its own is not what we want. We want to apply LoRALinear to an already pre-trained layer. And so we just need the ability to copy the weights from the original linear layer that was in the model that's already pre-trained and copy it into our LoRA layer. And so every layer in PyTorch basically has two attributes. It definitely has a weight and it might have a bias if it's there. So what we're going to do is just self.weight.data. Now self.weight doesn't exist yet in this class. It will exist when we actually write our layer classes. So self.weight doesn't exist yet. It will exist in the future. But for now, so we're going to do self.weight.data. It's just the state dictionary. And we're going to copy in the weight. So this is just going to be a dictionary with weight and potentially a bias. And so we're going to just copy our weight into our weight, just like that. And then we're going to do if bias in state dict.keys, right? Keys, if bias is available. Then we'll also do self.bias.data equals state dict bias, just like that. So this is just our base layer with all the methods that we'll be reusing for all the different stuff that we'll be doing, but we won't be using this method until the very end. And so we'll come back to it again then. So let's go ahead and write our very first LoRA layer. And once we do that, then once we do the linear LoRA layer, then the embedding and the convolution comes naturally from there. So let's do class LoRALinear, linear. And this is going to be a wrapper on the existing nn.linear module, but it's also going to, we also need to inherit LoRa layer base, right? So we have basically multiple inheritance happening here. It doesn't really change anything if you've never seen this before, but we can just add in a couple things. So what are the things that a linear layer has? It has in features. This is a regular linear layer, so we want to configure it the same way. We have in features, out features, we have bias, or bias is true by default, right? Do we want to bias? What is the rank? So let's say a rank of 8. And this is now, again, the LoRa specific stuff. What is the rank we want? What is the LoRa alpha that we want? What is the LoRa dropout that we want? Do we want to use RS LoRa? And then any other keywords that we pass in that we don't, keywords basically, that we pass in that we don't really care about, right? So this will just be any other arguments, keyword arguments that we pass in. It's just a catch-all basically, but we're not going to worry about it because these are basically the ones that we care about. So now that we have that, we can do, first we need to initialize our, so we have two things to actually initialize, nn.linear and the LoRa layer base. So let's do the nn.linear first. We're going to do nn.linear.init. All right, so we're going to initialize the linear layer, self, and we initialize this linear layer exactly how we initialize every linear layer. We have in features, we have out features, and we have our bias equals bias, and then any other keywords, right, that we passed in, but we're not gonna, that's again just a catch-all, so we don't have to think about it. And so that's our regular linear layer. And so now if we actually do if name equals main, and we do layer is equal to LoRALinear, right? And let's say we do an in features of 4, out features of 4, and print layer, we can then do Python LoRa. You'll see it's just a regular linear layer with, but it's called LoRALinear now. That's the big idea, which means once we've initialized linear, now self.weight, for example, so we can do print self.weight and print self.bias, right? The weight and bias of the linear layer are now pulled in because this is again just a regular linear layer. I'm just wrapping it with some additional logic. So again, that's how class inheritance works. And we get basically all the benefits and everything that exists inside this linear layer are now available to us as attributes in our class. So there we go. Those are our layers. Similarly, we need to initialize the LoRa base layer, right? So we're going to do LoRa layer base, and we're going to do dot init, and this will be self rank equals rank, LoRa alpha equals LoRa alpha, LoRa dropout equals LoRa dropout, and use RS LoRa, or use RS LoRa is equal to use RS LoRa. So this will go ahead and initialize my LoRa layer base, wow, tongue twister, and it'll basically get it working, and that gives me access to all of these things like self.scaling is now an attribute I have access to, but I also have access to this method here, which we're not going to use yet, but it's there. So this is just a regular linear layer with just some additional attributes so far, nothing crazy. Now, like I mentioned, the self.weight, so we can do self.weight. The weights of this linear layer is what we want to freeze, the weights of the original linear layer. We're going to freeze those weights, and we are going to train the new A and B matrices. So again, going back here, we want to freeze W, which is the weight layer. We also have a bias, right? A linear layer has a bias, and whether or not we train the bias layer is optional, and that'll be a toggle we'll implement later. But the weight layer of a LoRa layer has to be frozen, otherwise it doesn't make any sense. So we're going to go ahead and freeze it. So we're going to do self.weight, and we're going to do .requires grad, and we're going to set it to false, right? So this will definitely turn off the weight layer, so we don't do any gradient updates. Now what we need is, instead of training, remember delta W is A times B. A is a matrix that takes in 768 input, goes to R, and then B goes from R back up to 768. So we can actually do this in two ways. We can either have two linear layers to do this, like we could have two linear layers and no biases, right, to do this, or we can just use directly create weight matrices as parameters and then just train them that way. So we'll do it the easier way. We can do self.LoRA A, And this is going to be an nn.parameter, right? These are just going to be parameters. And for now, I'm going to initialize these as torch.zeros, and it'll have in features, right? So this is a linear layer that takes some input features, in this case 768, and some output features, which again is 768. So that's what this is. So that means my A has to take input features, compress down to R, and then B needs to take R and compress out to whatever the output features I specify in this linear layer. So we're going to go from in features down to rank, and then self.LoRAB is again nn.parameter, torch.zeros. And we're going to do from rank up to out features. And that's it. That is basically our setup of our two layers. And again, if you remember, a linear layer is just weight matrices, right? So these are my two weight matrices that'll take my in features, compress down to rank, take my rank, decompress back up to out features. And so we're good to go there. And this is one discrepancy that I noticed in the paper. They initialized LoRA with a Gaussian distribution. There's a Gaussian initialization for this. In the implementation I saw from Microsoft, they used chiming uniform instead, and they claim there's no difference in performance or results or anything meaningfully different. So I'm just going to stick to what they did, and it should be fine. So we're going to do nn.init.chiming uniform. Chiming uniform. And we're going to uniformly initialize self.LoRA. They leave LoRAB as 0. So LoRAB is left alone as zeros, but LoRA is initialized as chiming uniform. So there we go. And we can give it our scale factor. A equals math.square root 5 is what they use. So this is just based off their implementation directly. So I'm not really thinking too much about it. So there we go. We now have defined our parameters. Let's move this up. So we have a linear layer, and we have our A and B, and so all the pieces are set up. We have our weight matrix, which is frozen. We have our A and B, and now we just need to pass our data through it. How do we do that? We take X and pass it through the weight layer like normal. So pass it through this linear layer like normal. Then we take X and pass it through A, pass it through B, and then get our output. And then we add those results together, multiplied by our scaling factor. So we'll just do exactly that. We can do def forward, self, X, right? That's our input. And this is just going to be, let's call this orig layer output. This will be our original layer out. And we can use the functional form. So it can do f.linear. And in f.linear, we can provide it the input, the weight that we want, and bias equals self.bias. So this is just a, this is exactly the nn.linear. If you actually look at the implementation of nn.linear, they're using the functional form of the linear layer. And in the functional form of the linear layer, you basically provide it, okay, so I'm doing a linear layer with this weight and this bias, and this is my input. I could have also done it manually, right? Like I could have just multiplied my weight by X. I could have added the bias and be fine, but this is just a little bit quicker and cleaner than doing that. So there we go. We now have our original linear layer, and that's basically this part of the branch right here. So that's done. And so up next is doing the other part. Now there's a couple ways we can do this, but the easiest way is, let's go ahead. We know delta W is A times B, right? A times B. So why not, let's just go ahead and create delta W. Let's just do A times B and then multiply X by that. So let's do A times B and then we'll multiply by X, multiply by the scaling factor, and we'll be good to go. So let's do LoRA mult, right? Let's call it that, LoRA mult. It's just going to be self.LoRA A matrix multiplication with self.LoRA B. And that's it, right? So this is me doing my A matrix times by B matrix, which effectively creates my delta W matrix, right? My low rank approximation of the weights perturbations for our fine tuning task. So now that we have that, we can do times self.scaling, right? That'll be our scaling factor. And that basically covers everything, right? That's everything we need. And so all we need to do now is we have our delta W, right? So all we've done here is now created delta W. So we just pass X to delta W, and then that will produce our output, just like that. So to do that, all we need to do is we can call this low rank out is going to be, the first step is we actually apply a dropout to this just for overfitting purposes. So we can do LoRA dropout X, and we'll just multiply this by our LoRA mult. And this is fair game, right? Because let's say we had an input, actually let's just do an example. So we can create a random tensor, this torch.randn, let's say we have a batch size of 4, 16. Let's make this a 16 input, 32 output thing. And let's also make the rank equal 2, right? Just for just so we can see, and we can do layer and rand. So we can print here LoRAMult.shape, and we can print out the original, although not trainable, self.weight.shape. So if we take a look, we'll see that our LoRAMult is going to be a 16 input, 32 output. Now, notice that our weight is actually 32 by 16. Why is it flipped? And so this is a good question, and we'll actually have to deal with this a little bit later. But just to give you an idea, in PyTorch, for whatever reason, I'm sure there's a good reason for it, I'm just not sure. Before they multiply by x, whenever you do a linear layer, before we multiply x by a, they first transpose that weight matrix. So they first transpose the weight matrix, and then they do the multiplication. So we see it here, let's close it again. We see it here as a 32 by 16 matrix, but really it's a 16 by 32 because they're going to transpose it before they use it. So these two matrices are the same. It's the same shape. It's just one's transposed and the other one's not, but that's fine. I could have also equivalently done this the other way around. So LoRA at LoRA would have been the transposed matrix, but I find that I find it more confusing to do it that way, so that's why I'm doing it this way. So there we go. We now have everything we need. So if we print our LoRankOut.shape and we print our original output, RigLayerOut.shape, let's go ahead and delete these two. Then we see that we get the exact same output shape, right? They're exactly the same. And if they're the same, I can add them together. So this is where I will do. Our final output is just going to be our RigLayerOut plus LoRankOut. And I already have the scaling factor multiplied right here, so I don't have to do it again. And I return the output, and we are done, right? So this is LoRA, right? This is exactly what we have defined here. We take our original data, pass it through the linear layer, but in this linear layer, these weights are turned off, the gradients are turned off, so this will never be a trainable thing. And then we pass our data as well through our A times B layers, scale it, add it to the results, and get it, which is exactly the figure I drew here. Take data, multiply by these things, add it together, and you are done. So now that we have this is almost everything we need, but we need to implement one more thing called weight merging, or merging weights. And so this is an optional thing. We don't actually have to do weight merging, and in most cases you wouldn't do it, but it is important to be able to implement, so we're going to do it. Let's kind of talk real quick about what weight merging is. The idea is very, very simple. We have W from the original model, right? That's our original pre-trained weight, and we've trained A and B, which is delta W, right? We've trained A and B, which is our approximation of delta W. Well, if that's the case, if that's what we want to do, what if I just want W prime? If I want W prime, I need to actually do this like I need to take my original weights and add this to it. So I need to do this operation to create what the final weight matrix is. So that's the question. If I want to merge weights, instead of having this W here, the original weights, and this kind of extra A and B weights over here, instead of just having all this stuff, we can combine all of it and just produce the final W prime matrix. So we just need to put it all together, and that's simple enough. But we need to keep in mind that the weight matrix for PyTorch is linear layer is transpose. So we just need to do that transpose operation. So what we're going to do is def merge weights self. Actually, there's no x, just self. And what we're going to do is merged weights, right? How do we merge the weights? It's weights. It's just the formula. So it's going to be self.weight.data, right? It's going to be W plus our scaling factor, whatever it may be, times our delta W, which is A times B, right? So we're going to do that. Plus, let's close you, sorry. Plus our self.scaling times our self.LoRA at self.LoRA B. And that's it, right? That's all we need to do. Now, again, like I mentioned, self.weight.data is a matrix of output by input because PyTorch does the transpose. My self.LoRA at LoRAB is input by output because I did it this way. So because they're flipped, I just need to make sure I transpose this matrix just so it's the same as this one. It's just going back to what we saw just a few minutes ago, where the order of the weights is just different on how I did it versus how PyTorch normally does it. So we just have to transpose them to make them the same. And so these are our merged weights, and that's it. And so what we need to do now is construct what we have. What we've computed is W prime. We now have W prime, the merged weights of the original weights plus whatever our perturbation is. And what we need to do is construct a brand new linear layer that uses these weights specifically. So we're just going to create a new linear layer and then just copy these weights into it. So this is where we'll create a state dictionary. And this is going to be, we'll call it a weight because there's always a weight. And the weight is merged weights. And we can do if self.bias is not none, right? So if there is a bias in this layer, right, then we can go ahead and do state dict bias is going to be equal to self.bias, just like that. So this gives us our weight, right? A weight and a potential bias if it's there. Once we have that, we can create a layer called merged linear. It's going to be just a regular nn.linear, nothing crazy. And everything about this linear layer is same as the initial linear layer we started with. Still has the same in features, the same out features, all that stuff. So we can do self.in features, self.out features, out features, and bias is going to be true if self.bias, or if, not of, if self.bias is not none, else it's false, right? So this is a new linear layer, right? A brand new linear layer that we just created. And what we need to do now is take the weights and biases, which is stored, and the weights are the merged weights and the bias. We're going to need to take all this information and just put it inside this new linear, because again, when we created this linear layer, this one's randomly initialized, right? It's just we just created one. It's randomly initialized, so we just need to copy our weights and bias into this new one, and that's easy. We can do merged linear dot load state dict and the state dict, and we will then return this new merged linear. And so how we use this will again become really important when we implement model saving and weight merging just a little bit later. But regardless, this here is a fully functioning LoRa layer, right? Fully functioning LoRa layer. So let's go ahead and test it real quick. Let's call this the output. And let's just print out the output real quick. Print output. And let's do smaller matrices, just so it's easier to see what's going on. Let's first make sure the forward method works. So we should get a 4x4 output, so we're good there. And now the question is, if we do weight merging, right, when we merge our weights together, the new linear layer we get from weight merging should give exactly the same results as doing it without merging, right? So me doing this pass, x through w and a and b, and getting the final result should be equivalent, right? These two things, just passing it through the merged weights, should be identical. So we're going to verify that now. So we have our output, layer n. So this layer is the LoRa layer. We're going to call this now merged, and let's call this that layer that we created. And we're going to do dot merge weight. So this will return. So merged is a new linear layer with the merged weights of the original layer and stuff. And again, this isn't a fair comparison because LoRAB is technically just 0 right now. So everything would be 0. So let's just initialize LoRAB as something. And we'll delete this after because we're not supposed to do that. But this is just for testing, right? So LoRAB, we'll also just initialize it in some way. And so now we have merged. And what we can do is output 2 is our merged layer. And we can pass in, again, the same rand input. And we can print output 2. And what we're hoping to see here is that the outputs are the same. And we can see there, sorry, 1.0590, 1.0590. Negative 0.68, negative 0.6. So we can see whether or not we're doing the LoRa operation or we merge the weights and just do a regular linear layer, we get the same results. And that's good to see. So that covers a full implementation of a LoRa linear layer. And so now that we've done LoRALinear layer, it's time to start moving into the other layers, but the other ones basically are exactly the same. They just have their own nuances here and there. So let's start with the next one. So we're going to do class LoRA embedding, LoRA embedding, NN.module. We're going to do NN.embedding. So this is going to be a wrapper on the embedding layer, and it's going to be a wrapper on the LoRA layer base, right? So we can pull all that stuff in. Now, one thing to keep in mind about the embedding layer is that when we actually do embeddings, remember, the thing that goes to embeddings are tokens, right? We're going to be passing tokens to the embedding layer, and then the tokens are converted to an embedding, right? The other thing to keep in mind is, as far as I can tell, in most implementations out there, typically the embedding layers are frozen and they're not trained with LoRa or something like that. So maybe you won't see this used as much, but it is good to just understand how we could potentially build something like a LoRA embedding layer. I'm going to copy this next stuff because it doesn't, it's exactly the same as before, right? So we have everything's the same, except in an embedding layer, we have our number of embeddings, which is our vocabulary size, right? How many possible words do I have in my tokenizer, for example? And then the embedding dim. How many numbers do I want to use to represent every single word? And so what would LoRA look like in an application like this? So let's go ahead and do self.wait, right? So actually, yeah, so self.wait dot requires grad is false, right? We don't need to compute gradients on the original embeddings. What we're going to do is create a new, and we can just do this again. We're going to be creating a new LoRA and LoRA but we don't really have input features in rank anymore. So let's kind of get an idea of what an embedding layer again does. So what we have is a weight matrix. Let's do this in orange. We have a weight matrix, and it's going to be n number of tokens by embedding dim, right? The number of numbers we use to represent every single token. So it'll look kind of like this, right? ... So that's our data. And how tokens work, right? We pass in the tokens like 2, 7, 1, whatever. And so we go and grab the embedding 2, right? So this, when we pass it here, will create a a matrix of the second embedding, the seventh embedding, the first embedding, right? That's our embedding matrix. So we go from tokens to embeddings for this application. So what would a LoRA look like for this application? If I wanted to, again, fine tune this model or this specific embedding layer, there is an n by e big matrix here. And again, if we take a tokenizer like the RoBERTa tokenizer, we're looking at roughly 50,000 possible tokens times 768 embedding dim. This is actually one of the biggest matrices in your neural network and requires a lot of parameters. So what if instead we do LoRA like this? So the LoRA part of this will be, instead of training it to be n by e, and let's just erase. We can leave that. That's fine. That's fine. Let's do the LoRA layer now. What we're going to do is we're going to have a input. The input is still the number of tokens. So what we can do is create a LoRA layer kind of like this. N by R. It's an n by R embedding. So this is still an embedding, right? Still an embedding matrix. But R should be sufficiently smaller than E. So what we're doing is we're taking tokens, right? And we'll produce embeddings that are going to be, again, E2, E7, embedding 1, whatever. And this thing has a dimension of R, right? Because each vector, each token, is represented by R numbers. That's the rank. And as long as R is smaller than this, then this matrix will have a n times R number of parameters, which should be much smaller than n times e as long as R is small enough, right? So there we go. This one has e parameters, right? E parameters that we're using to represent everything. And so now that we have this, so the first layer, this is A in this case, so this will be our A matrix. That A is basically just a smaller embedding matrix. That's all, a smaller dimensional embedding matrix. So same number of input tokens, we can't change that, but R is smaller than E. And now that we have that, we can now create our B matrix, which will look kind of like this. It's going to take R inputs and produce E, because we have to get to E, right? Get to E. It'll produce E outputs. And this will basically project each one of these tokens, which are represented by embedding DIMMs of R, and project them up to our final embedding. So E2, E7, E1, just like that. And this is E, right? Or uppercase E, just to keep it consistent, right? Uppercase E. And then we can take these two matrices, add them together with the alpha over R scaling factor. And that's it, right? So exactly the same. The only difference now is we will have this n by R matrix here. That is an embedding matrix. It's just a regular embedding matrix, just with an embedding dimension much smaller than E. So R much smaller than E. And then we take each of these and project them up. So you end up with, initially you had 50,000 by 768. Now you'll end up with like 50,000 times maybe R could be 8, for example, plus whatever R to 768 is, so plus 8 times 768, which this is a heck of a lot smaller than 50,000 times 768, right? So again, this is same idea, just applied in a slightly different way because we're dealing with an embedding matrix here rather than a linear layer, but same principle. So let's go ahead and implement this. Let's go ahead. Where are we looking at? Here we go. So first of all, how many inputs do we have, right? So again, A will have n inputs with an embedding dim of R. So basically every embedding matrix, if you remind yourself, if we print self.weight.shape, let's do LoRAEmbedding. And let's say we have a vocab size of 200, and each vocab is represented by a dim of 64. Let's just say that for now. And for the rest of the stuff, we can just comment it out. And so when we do this, you'll see that it is a 200 vocab size by 64 matrix, right? 200 by 64. What we're going to do is create an A with a rank that's smaller. So this will still be vocab size. So this will be num embeddings or vocab size, whatever you want to call it. And it's going to go to a rank. So now we can do print self.LoRAA.shape, right? And it'll be 200 by 2. So we're now representing, instead of every number with 64 numbers, we're representing every number with just 2 numbers, for example. And so that's our reduction in size. Now that we have that, we now need our LoRaB, which will take the rank and project it back to the embedding dimension that we want. So there we go, right? That's our setup, LoRaA, LoRaB. And just like before, we want to initialize with the Kaiming uniform on LoRaA. So let's go ahead and do that. So that's our initialization. So this is the start to our LoRa embedding. And like before, we need a forward function. And this forward function will look basically like our previous forward function. But we can use a little bit of help from PyTorch actually to do this. So first of all, orig layer out. So this will be the output of this original branch. So we're going down this branch right here, the original branch. Let's go ahead and do that. We can use, just like we did f.linear last time, the functional form of the linear layer, we can do f.embedding this time, the functional form of our embedding layer. And the input is equal to x. And this is obviously expecting basically tokens or long tensors, right? So integer numbers for these things. And let's just fill in the rest. The weight is going to be self.weight, right? So that's the weight matrix that we want to effectively index in our embedding layer. And then the embedding layer actually has a bunch of other pieces of information. All of this information was initialized when we created this. It exists inside the kwargs, right? If we had actually passed them in. So they're all there, but we don't typically use this stuff. By default, like we don't really think about it all that much, but they're always there when you define an embedding matrix. So we have to include it here. So padding index is going to be self.padding index. Our max norm is self.max norm. That's our max, that's fine. Norm type is equal to self.norm type. Scale grad by frequency is going to be, is self.scale grad by frequency. And then sparse is equal to self.sparse. So again, this is just extra information that the f.embedding needs. It was already defined here by our nn.embedding. It's in the initialization. We're just because we didn't specify it, all of this stuff is just whatever's default, and that's fine for us because we typically use the defaults anyway, so we can kind of just ignore it. We don't have to think about it all that much. Now for the next part, we're going to call this low rank out or low rank A output. Again, f.embedding. So we're doing the same f.embedding. Let's actually just copy this, right? We're doing exactly the same operation as before, but instead of doing it on this big embedding matrix, right? Cancel. We're going to be doing it on this smaller one, right? So what did we call the smaller one? We called it self.LoRA A. So we want the weight to be self.LoRA A, but everything else is the same, right? Nothing else changed. So we're just doing the same embedding of the same X, but we're doing it on our LoRA A matrix, which has the same number of embeddings, but the embedding dim is significantly smaller than the original weight matrix. So that's it. Now that we have that, all we need to do is low rank output, right? Is just going to be our low rank A output at, right? So this will end up being a, like we saw before, a sequence length by R. And so we're going to multiply it by a R by embedding dim, right? R by embedding dim, and that'll, the shapes already work out. So we just do at self.LoRA B, and we do times self.scaling, and we are done, right? So that's our setup. And now that we have our LoRA, we have our scaling, we add the initial input to our kind of scaled input, right? So that's all we have to do. So our final output is going to be a rig layer out plus low rank output, return output, just like that. So that goes ahead and completes our forward function. So again, looks very familiar, basically the same as the linear layer, just have that extra nuance that we're actually dealing with the embedding layers. Also, the other thing is, notice that in the linear layer, we had a dropout. Here we don't have a dropout because X is tokens, right? They're literally just raw tokens coming out of our tokenizer. That's not something we would ever apply dropout to, so that's why you don't see any dropouts here. Now that we have that, we need to write, again, the merge weights function. And let me make sure I made it plural in the first one. Weights. Yeah, merge weights function. So again, we need to be able to merge the weights. Merging the weights here is pretty straightforward because all the shapes are, why do I keep doing that? Sorry. All the weights, the shapes of the weights are all the same. So we just kind of do it. So we can do merged weights is going to be self.weight.data plus self.scaling times self.LoRA A at self.LoRA B, right? Because I have a num embeddings by rank times a rank by embedding dim. And so the effective matrix is num embeddings by embedding dim, which is the same shape as my self.weight.data, right? So that's our setup. Now the thing of, again, we had to do the transpose up here because self.weight.data is transposed in the way that PyTorch does it, but the embedding layer is not transposed. It is what it is. So that's how we're doing it. The embedding layer has no bias. It's only weights. So all we need to do is create a quick state dict. It's just going to be a dictionary of the weight with our merged weights. And just like before, what we're going to do is create a brand new embedding layer. In this case, merged embedding is going to be nn.embedding self.num embedding self.embedding dim, right? So there we go. We've just created a new embedding matrix that looks just like the previous one. And now we just want to copy our merged weights into this one, just so we have that final, again, just recapping, W prime, right? Because W is our embedding layer. We trained an A and B. We want to put them together so we get our final W prime and don't have to deal with all these different weights. We just have one weight for everything. So we can do merged embedding dot load state dict, and we can return merge embedding. And there we go. That effectively covers or completes our LoRA embedding layer, right? So we have LoRALinear, we have LoRA embedding. Now we have the LoRA convolution, which is actually the most challenging. It's not hard. There's just a little bit, a couple more pieces of nuance that we need to deal with. So let's go ahead and do it. Class LoRA conv2D. And this is going to be a wrapper on the existing nn.conv2d. And again, our LoRA layer base. Again, I'm just going to copy all of this because it's exactly the same thing as before. Let's copy it. So just like before, a convolution layer, there's an in channels, out channels, kernel size, stride, padding. There's other stuff, right? Dilation, and that would be passed in the kwargs, but I'm not going to go into too much detail here because, again, this is just for teaching purposes, so it's fine. So we have all of our standard convolution stuff, and then we have all of our LoRA stuff. And so I've gone ahead and initialized my convolution and my LoRA layer base. Now, the part that makes this challenging is actually the shape of our layer. So let's go ahead and take a look. So let's say in channels is 3, right? And then we can do out channels is 32, let's say. And we have a kernel size, and let's say we do a 3x3 kernel size. So let's just take a look at what the shape of the weights look like. Print self.weight.shape. And if you haven't ever looked at this, it is intuitive, but it requires a little bit of thought. Actually, let's pick different numbers here. Let's do a kernel size of 4. Otherwise, everything will be the same. So we have a 4x4 kernel, right? A 4x4 kernel. 4x4 kernel. And we have 3 input channels, and we have 32 output channels. And this is the key idea that I want you to take away, where really there's, again, if you watch my intro to convolution video, you'll know that convolutions are actually just linear layers, just applied in a slightly different way. I won't go into too much detail about that right now, but the easiest way to do LoRA on convolutions is by messing with the channel dimension. So what I mean by this is, let's pretend you had a convolution layer in your model that went from 256 channels to 256 channels, right? So you'd have 4x4 kernel, you go from 256 channels to 256 channels. So there we go. And so this model here would have, let's say Python, we'll do 256 times 2, or sorry, this layer here would have 256 times 256 times 4 times 4 number of parameters. So we're looking at about 1, 2, 3, 1, 2, 3. So about 1 million parameters inside this one layer. So that's quite a bit, right? That's a lot of parameters in a single layer. And so if we had to train it, we'd have to train all these parameters and all those problems. What if instead we changed our problem to go from, instead of going from 256 channels to 256 channels in A, let's draw this out. So our target is to go from 256 channels to 256 channels with a 4x4 kernel size. And this is roughly 1 million parameters, right? What if, so that's our original convolution. What if we go from 256 channels down to, let's say, 4 channels, because that's our rank. And then we go from 4 channels, and then we go from 4 channels back up to 256 channels. And all of this was with a 4x4 convolution, right? 4x4 kernel. Now this isn't exactly how we're going to implement it, but that's the main idea. So so actually this one here will be a 4x4 kernel. And then here, so here the 4x4 will go down from 256 down to 4 channels with the 4x4. But all we want to do in the next step is just upsample the number of channels from 4 to 256. So this one we can use a 1x1 kernel. Because if you remember, so let's say we start with a batch by channel by height by width, right? And the original, let's say the original one, the original convolution, let's do the actual numbers that we have. We'll start with batch by 256 by height by width, whatever it may be. Let's say we did a convolution with a stride of 2. Then we would end up with a batch by 256 by height over 2 by width over 2, right? That's the setup. We're just, that's what this convolution would have done, right? That's what this, because we're going from 256 to 256 with a 4x4 kernel and a stride of 2. So if we do a stride of 2, our height and width will be roughly half on the other end. So there we go. Now, how do we do this with our second one? Okay, well, the first convolution, we're going to go from 256 channels to 4 channels with the 4x4 kernel. But let's say we do the stride of 2 right here. We'll do the stride of 2. So everything else is the same. Everything between these two convolutions is identical except the number of output channels. But everything else is the same. So that will produce a batch by 4 because we went from 256 channels down to 4 channels. But because we did a stride of 2, right? The stride has nothing to do with the number of parameters. The stride is just how the kernel is moving. So we'll still have a height over 2 by width over 2, right? Just like that. And now that I have a batch by 4 by height over 2 by width over 2, and my final target is batch by 256 by height over 2 width over 2, all I need to do is make my 4 a 256. And there's 2 ways we can do this. We can apply a convolution with the 1x1 kernel and a stride of 1. A 1x1 kernel will effectively take this, allows us to change the channel dimension without changing anything else. You can look at some of my previous videos or just look up why we use a 1x1 kernel, but that's effectively always the purpose of a kernel size of 1, because a kernel size of 1 changes nothing about the height and width, because these two things are already the same, and it just changes the number of channels to whatever the output channels we are. Doing a kernel size of 1x1, doing a 1x1 kernel is actually the same as just doing a simple linear layer. So we can also reshape this. We can do batch by and just transpose some dimensions around. Height by 2, width by 2 by 4, right? So we're taking this 4 dimension, moving it to the end. And then we can multiply this by, we can do matrix multiplication with our B matrix, which is going to go from 4 to 256. So B will be a 4 to 256 matrix. And that'll take this 4, make it 256. So this will become I'll write it right here. It'll become a batch by height over 2 by width over 2 by 256. And then I can transpose it again. So I can go back to 256 by height over 2 by width over 2. And so now these two things are the same. So both options are valid. We can either use a 1x1 kernel thing, or we can do a linear layer. And we're going to use a linear layer just because it's easier. So let's go ahead and implement that. We'll kind of reference this as we go, so it'll make a little bit more sense if you're confused at all. So to do this, just like before, we need to do self.wait.requireScrad is false, right? Because we don't want to train anything. And so our self.LoRAA is going to be an nn.parameter, torch.zeros, and we will pass in, and the way we're going to do this, right? The key idea, if you again remember, the shape of the weight matrix for a convolution layer is out channels. So it'll be out channels by in channels by the kernel height by the kernel width, right? And so I want to go from in 256 to out 256. That's my initial layer. Right now, we're going to go from in 256 to some lower rank right now, right? And this weight matrix is basically my convolution going from input of 256 to output of R. And that's the key idea. So let's go ahead and do that. We could have also done this by just defining a convolution layer, but we're trying to stick to the implementation as much as possible. So again, we're going to initialize this as torch.zeros, and the shape is going to be rank by self.inChannels by our self.kernel size just unpacked, right? Kernel size unpacked, because if you just pass in one number, this is automatically converted to a tuple, and then this will just be 4 by 4, just like that. So this is our layer. It is our out channels, which will be rank in this case, by 256, which is our input channels. And then we have our kernel size. And then self.LoRAB, again, we could have done this 2 ways. We can either do it as a linear layer that projects from rank up to self.out channels, or we could have done it as another convolution layer, which would have looked like this. Be nn.parameter, torch.zeros, and we want out channels, so it'd be self.out channels rank 1 by 1, right? This would have been the shape if we wanted to use a 1 by 1 convolution. This is the shape if we want to use a linear layer, and we want to use a linear layer, but either one would have worked just fine. So we're just going to go with linear layer today. Again, same initialization, right? We're just going to use Kaiming uniform. So there we go. Let's grab you. There we go. And so now let's go ahead and do our forward, and then we'll do our merge weights, and then we'll be done with writing all of these LoRa layers. So self X. And so how do we do our original layer? We just pass our data through. So we're going to do a rig layer out is going to be f.f.conv2d. We're using the functional form. We're going to do input equals x, weight equals self.bias, bias equals, or sorry, weight is equal to self.weight, weight, bias is equal to self.bias, stride is equal to self.stride, and padding equals self.padding, right? All the, I know there's more stuff in a convolution you can have, but those are all the things we care about right now, so that's all we're going to have. So there we go. That is all of our convolution stuff. And this will be the original convolution. So let's go ahead and do an example. So we're going to do rand is equal to torch.randn, and let's just make the typical shape. Let's do a batch size of 4. How many input channels do I specify? 256, so 256 channels. And then let's say we have a 64 by 64 image. And so we're going to do layer, rand, and we can print out now, print or rig layer out dot shape. And we'll see that, exit. This will give us exactly what we want. Looks like torch.zeros. Whoops, my bad. So we have a 4 by 256 by 61 by 61 because, you know, because with the stride and both the stride and kernel size and padding that we picked, we had some downsampling on the image. That's fine. But notice our channels went from 256 up back to 256. Just to make it more different, we can make this 384 maybe. And now we can see that we go from 256 up to 384, but the height and width, right, is the same. So now let's do this with our low rank matrix. So how this will work out is going to be LoRA rank or LoRA rank a output. Again, this is just because I set up my weight matrix in the shape that a convolution expects it. I can just go ahead and use it. So conv 2D, and actually let's just print out really quick, print self.LoRAA.shape, just so it's clear, right? So LoRAA, LoRAA is a 8, so 256 input, we have a rank of 8 by default, and then a 4 by 4 kernel size. So this is the weight matrix that we're going to apply. Earlier, right, the original weight matrix, so self.weight.shape, and let's get rid of you, just so you can compare. The original weight matrix goes from 256 up to 384 channels with a kernel size of 4 by 4. My new LoRA matrix is going from 256 down to 8 channels with the 4 by 4. So again, very, very similar, but we can now use it identically. So I can actually just copy this in, right? Everything else is the same. Oops, my bad. Let me fix that. There we go. All right, so we have everything we need, except our self.weight is not going to be self.weight. It's going to be self.LoRAA, right? Self.LoRAA. And when we're doing this LoRa layer, there is no bias, right? LoRa doesn't, there's no bias in the LoRa layer. There's a bias here, but none specifically in the LoRa layer. So there we go. So no bias, but we want to make sure it's the same stride and padding because everything else about the convolution has to be the same. It's just all we're changing is how many channels we're projecting to, and we're doing less channels is the idea. So now we have our low rank A output. And so if we print our low rank, or sorry, LoRA rank A output, let's get rid of these two. We don't need them anymore. There we go. We'll see that we have a 4 by 8 by 61 by 61, which is the same as, remember, before we had a batch size of 4 and we projected to a 384 by 61 by 61. Now we still have the same batch size of 4, but we projected just 8 channels, but the 61 by 61 stays the same because I kept everything else about the convolution the same. So now we're good to go there. And now is this manipulation that I talked about. So we have a batch by rank, by height, by width, whatever it was. And so I need to move the 4 to the front, that's here, and then multiply it by our LoRa B to project our 4 channels up to the however many channels I want, in this case, to 256. And then I can just take that and just put it back how I found it. The other option, again, to project the channels how we want it is just using a convolution layer, a 1x1 convolution layer. But that's okay. You can do it however you want when you implement it yourself. I'm just going to do it this way because it's easy. So what we can do is low rank A output is going to be, or no, keep doing that. LoRa rank A output is just going to be our LoRa rank A output. And we don't need these parentheses. So let's look at the shape real quick. This is dimension 0, dimension 1, dimension 2, dimension 3. So we want 0, 2, 3, and then 1, right? So 0, 2, 3, 1 is the pattern. So we can do dot permute. Permute, it'll let us move all our dimensions around. So we can do 0, 2, 3, 1. Print LoRa rank A output dot shape. Let's just keep track of it as we go. And now we have 4 by 61, 61, and we moved our rank dimension to the end, which means now we can go ahead and do the multiplication, right? Go ahead and do the multiplication. So let's do that. We need to do LoRa rank A, actually this final low rank output is going to be self dot LoRa dropout, just like always, on the LoRa rank A output. And we're going to just multiply at self dot LoRa B and multiply by the self dot scaling factor. So now if we take a look at our low rank output, you will see that we have, that's not helpful, shape. And of course everything is 0 because B is 0, but let's ignore that. 4 by 61, and now we've projected those 8 up to the 384 channels that we want. So now what I need to do is just take the 384 and put it back where the channel dimension normally goes, right? Just put it back how I found it. So we can do low rank output is equal to low rank output dot permute. And again, the shape will be, now we want the 0th is the same, and then take the last one, the second last one, and there we go. 0, 3, 2, 1. Actually, no, sorry. 0, 3, 1, 2. We want to keep those dimensions the same. So that'll be 0, 3, 1, 2, right? So we're just changing it around. Good. And so our final output is just going to be the original layer output plus the low rank output, and we return the output. And we are done with our forward function. Good. And so now that we have that, let's just make sure this runs without error. Yeah, this looks like it's good. So now that we have that, we can go ahead and write the weight merging, right? So one more time, merge weights self. For that. There we go. Again, weight merging is almost identical, but there's a little bit of a tensor manipulation that we have to do just to pull it off. The problem is that we have, let's just look at our weight matrices real quick. We have our weight matrix here. Okay, so currently, let's just use the numbers themselves. We have a 8 is our rank. So this is LoRa A, right? So A. 8 is a 8 by 256 by 4 by 4 weight matrix, right? That's basically what we created up here in LoRa A. And then LoRa B is just a, whatever the rank is by the output channel. So this is going to be 8 by 384 in this case, right? Because we set the output to be 384. So what we need to do is multiply this by basically what's the final one we want? We want 384 by 256 by 4 by 4. This is the final shape that we want for our convolution layer, right? 384. The only way to, there's obviously a couple ways we can do this, but we can first do our, we can multiply LoRa B. We can take the transpose. So we can do, for example, LoRa B transpose will be, so this is B transpose. It will give us a 384 times 8 matrix. That's the first one. And then we can multiply it by A. And A is an 8 by 256 by 4 by 4, 4 by 4 tensor, right? So there we go. And this will give us, right, this 8 and this 8 match. So doing this matrix multiplication will give us the final shape that we want. Now, the only thing is that in PyTorch, you can't actually do this matrix multiplication. This will only work out if this is a two-dimensional tensor. So what we're going to do is take this 256 by 4 by 4 and just flatten along this dimension. Flatten. And so we'll end up with an 8 by 256 times 4 times 4. Just for now, we're going to put it back. And then we're multiplying basically a matrix by another matrix. So this will end up being when we do this multiplication, 384 by a 256 times 4 times 4 matrix. Again, it's exactly the same thing. I've just flattened this dimension just so PyTorch is happy with this matrix multiplication, because it wouldn't be happy otherwise. So there we go. And once we have that, we can then unflatten this back to 256 by 4 by 4 to get our final shape. So that's basically the couple of little operations. I'm sure there's another way of doing it, but this is the way I'm doing it, so it's probably fine. So we need to do LoRA flatten, right? We need to flatten these last 3 dimensions. So let's do that. It's going to be just our self.LoRA.flatten everything after the first dimension, right? We want to flatten everything from the first one to the end. So ignoring the 0th dimension, basically. So there we go. And then we can do LoRA mult is going to be self.LoRAB. And like I mentioned, we have to transpose it. So the rank dimension is last. So we have to do transpose. So LoRAB transpose at LoRA flatten, and then times self.scaling, like always. And LoRA mult is now this, right? This shape here. And now we just need to take the dimensions that we flattened, and just reshape them back to how we found them. So this is going to be LoRA mult. It's going to be LoRA mult.reshape, and the shape should be self.out channels by self.in channels by, and we can just unpack our self.kernel size. So there we go. And so our final merged weights is going to be self.weight.data plus LoRA mult, right? Everything else is the same. We're good to go. Because the shapes are now the same. We're at the shape that we want, which was the original matrix that we wanted, tensor that we wanted. And so we're good to go. We can add them together. And now, just like before, we have to do the state dict, right? We are going to create a brand new layer, a brand new convolution layer, and just copy our data into it. So we're going to do merged conv is going to be nn.conv2d. It'll have self.in channels, self.out channels. It'll have kernel size is our self.kernel size. Our stride is self.stride. Our padding is self.padding. And bias is again true if self.bias is not none. Otherwise, it's false, right? So there we go. I've created my convolution. We also have to create our state dict. So we can do state dict is our weight matrix, which will be our merged weights. And then if self.bias is not none, so if we if our bias is not none, we can do let's move this up one. State dict bias is equal to self.bias, and there we go. We now have everything we need in our state dictionary, so we can go ahead and just stick into our merged conv dot load state dict, and we are good to go. We're now loading our merged weights into a single convolution, and we can return merged conv, and that effectively completes all of our LoRA layers. So we have here, again, just as a quick recap, we created a base layer that just contains all the stuff that shows up in every single LoRA layer. And then we created a LoRALinear layer, a LoRAEmbedding layer, and a LoRAconv2d layer. And each of these layers have the ability to merge weights, which we'll see why we do that a little bit later when we actually implement model saving and that sort of stuff. So now that we have this, we have the next important step of our implementation, and that is we need to be able to take an existing model with linear layers and convert them to LoRALinear layers, right? That's basically the main goal here. All we've done is construct some layers. We haven't written any of that logic to actually convert existing layers to these LoRA layers. So to do this, there's a couple steps that we have to take. I'm going to import here from transformers, import auto model for sequence, auto model for sequence classification, right? So I'm just going to be loading a existing RoBERTa model. And we could have also used my RoBERTa implementation, but it's fine. This is just supposed to be easy. So we're just going to load an existing RoBERTa model, and then we will we'll see what we need to do to basically update all the layers in that. So let me grab the name. It's called this. So there's a RoBERTa model. Let's print out the model real quick, just so we know what we're working with. So here is an example of a language model, right? I mean, it doesn't have to be a language model specifically, but this is a model, right? And it's a RoBERTa model. It has embeddings, it has transformer layers, it has attention, it has all these linear layers in it, has all this stuff, right? So this is effectively my language model that I want to, let's say, fine tune, right? Because what I've done here is load a pre-trained language model. But what I want to do is now fine tune it. And so here's some of the key ideas when it comes to, again, fine tuning. And typically, all of these weights here are pre-trained with that mass language modeling task. These weights here are randomly initialized, right? We added a new classification head to actually do the classification task that we care about. And so in traditional fine-tuning sense, we could have either A, fine-tuned the entire model, but that could risk things like overfitting and things like that if you don't have enough data. Or we could freeze the entire backbone, not train anything here, and we can just fine-tune the classification head, but that typically doesn't lead to as good results, again, as long as you have sufficient data. So basically, for us to do LoRA, to convert this model to LoRA, there is 2 steps that we need to do. Number 1, we need to identify which layers do we want to convert to LoRA. So I'm going to be doing it by name, which is how Huggingface does it. So like I want to convert the word embeddings to LoRA. I want to convert the query keys and values to LoRA. So what we want is, instead of a linear layer for query, we should have a LoRA linear layer for query. And that means, and so that's step 1. And then again, dense layer, all these linear layers. The next step is, when I change this linear layer from a linear layer to a LoRA linear layer, I need to, number 1, I need to convert this to a LoRA linear layer, but I also need to copy the weights that's already inside this linear layer into my LoRA linear layer. Because the LoRA linear layer, right, when we look, again, tongue twister, this LoRA linear layer, this self.weight here has to be the pre-trained weight. So we need to copy from this linear layer, the weights inside this thing, into here. And so that's another step that we have. And that's exactly what we're going to be using this load pre-trained weights for. It will basically take weights from one layer and just copy them into our LoRA linear layer. So we'll see how we do that in just a bit once we get there. So for now, I'm going to copy a couple things in. So the first one is the LoRA config class. This basically has nothing in it. It's just telling me that it's just all the information that we had before, right? LoRA alpha, bias, dropout, rank. But we include these 2 new things here called target and exclude modules. So let's talk a little bit about what that is. And it'll make most sense if I actually copy my target and exclude modules in. So let's do that here. Let's actually do it underneath. There we go. There we go. So the target modules is, I want to apply LoRA to every query, key, value, dense, and word embedding layers. So all layers that's called those things. So that means every single QKV and dense, these dense layers, will be converted to LoRA. This word embedding layer will be converted to LoRA. Now in the exclude modules, I have classifier. Remember, the classifier has not been trained yet. It's randomly initialized. So LoRA only works on a layer that has been trained, like a layer that actually has pre-trained weights. When we haven't even trained those weights, we just want to train them traditionally. We don't need to do any LoRA on them. So we want to make sure anything underneath this classifier branch is excluded from LoRA. And so that's what this is for. So using kind of this information, let's go ahead and start building out what this function looks like. This everything we're about to do is not tough. It's just more tedious than anything. So let's just do it. So we're going to do class LoRA model, and this is going to be a regular nn.module. It's going to be a regular model. It's going to take our existing model and basically convert it to a LoRA model. So let's do that. So again, def init self. We're going to pass in the model. So this would be the model we want to convert, in this case, RoBERTa, and also the config, right? The configuration of LoRa that we want to use. So let's go ahead and define this stuff. So first we have our config. It's going to be LoRa config. And let's just set the target modules equals target modules and exclude modules is equal to exclude modules, right? So everything else can just stay default. Right, there's also this bias term, which I forgot to talk about. Like I mentioned, the biases, every layer has a bias, and it's completely up to us if we train them or not. None would mean turn off all the biases in the model. We don't want to train any of them. And that's pretty typical. All means we want to train all the biases in the model. And so that's fine. This I don't ever really see anyone use, but it's there. And then lastly, we have LoRA only, which means I only want to train the biases on LoRA layers, but everything else should be frozen. And so again, we'll kind of deal with that in a bit. For now, this is fine. And let's just actually set the bias to LoRA only, right? Let's just do that. So now what we can do is create our LoRA model, and that's just going to be our LoRA model that we're defining here. And we pass in our model and the config, right? And so now that we have that, we can start doing some stuff. So let's go ahead and just like every model, super LoRa model self.init, right? So there we go. Self.LoRa model is our model, and self.config is equal to our config. So there we go. Now I will do a quick sanity check here. In this case, I passed in the classifier. It's a list, right? But I could have also just done this, right? Just passed in the text classifier, just so it's always the same, no matter how you pass the text in. I'm gonna just make sure it's always a list. So what we're gonna do is just some sanity checks. We're gonna do if self.config, right? Self.config dot target modules is none, right? If it's none, so we never passed in anything for the target modules, which means we're not really, I don't know why you would even use LoRa in that case, but there we go. If it's none, then we're gonna do self.config dot target modules is just an empty list, right? It's an empty list, and we'll just keep it like that. Elif is instance, right? We're gonna do self.config dot target instance target modules. If it's a string, like we just passed in a string, then we do self.config dot target modules is going to be just a list with that one thing in it. Config dot target modules. So it's just a sanity check to ensure that it's always a list. Either it's an empty list or it's a list with just that one string in it. But other than that, we're fine. So let's go ahead and do this again. And not just for the target modules, we're also going to do it for the exclude modules, right? Exactly the same thing. We'll do it for the exclude modules to make sure. So this way, whether or not we pass in classifier as a list or pass it in as a text, then it's always going to be the same. So for step one is let's go ahead and compute how many trainable parameters our model has currently, right? Before we do any LoRa, how many trainable parameters do we have? So we're going to do arig trainable params is just going to be self dot, and we're going to write a method called compute trainable parameters, right? So let's go ahead and write that. Def, let me just make sure I'm looking at the right place. So this is going to be def compute trainable parameters self. And so let's see, we're going to do total learnable parameters is just 0, and then we're just going to loop through a model for param in self.LoRa model dot parameters, right? Looping through. All we need to do is if param dot requires grad, if it's true, right? If it requires grad, actually we can just do that. It's already a flag. Then we can do total learnable parameters is param dot number of elements in it, and we can return total learnable parameters. So that's it. So it's just going to loop through a model, count up which parameters are trainable, and just add them up. And we're going to use this method later again when we're done with LoRa, right, to see how many trainable parameters are left. So there we go. That's step one. Now that we have completed computing the trainable parameters, the next step will be to disable all gradients. So by default, when we do LoRa, regardless, so for example, let's say we were only doing LoRa on the queries, right? Only on the queries, and everything else was not LoRa. So our target basically our target module in this case would have just been query. That means we only want to update the query vector or the query linear layers, and everything else must be frozen, except of course the classifier, right? Except the classifier. The classifier always has to stay. So what we want to do is disable gradients on everything except the things that are in the exclude modules, right? So to do this, we're going to write a quick helper function. And this is going to be to check by name. Actually, maybe I can write that in a second when it starts to make a little bit more sense. So let's write a function here called def disable all grads, right? We're going to just write a function here that's going to disable all our gradients. It's going to be for name param in self.LoRAModel.named parameters. I'm going to loop through all of them. And let's just print out the name real quick. Just print out the name, and we're going to run self.disable all grads. And hopefully this will print out all of the names without any error. So there we go. These are all of the layers in this model. And what I want to do for now is disable gradients on everything except, of course, the classifier layers, which is in our exclude modules. So we need to check if classifier, or really if we had a list of stuff in here, if any one of these names in our exclude module is in this name, right? So we just need to do that. So to do this, we're just going to write a quick helper function. We're going to do def, what did I call it? Just so I keep it the same. So we're going to do exclude module name check. So it's going to take self, and it's going to take a name. So it's going to take a name of a layer. And what we're going to do is return if there's, so we're going to do exclude for x in self.config.exclude modules, right? So what we're going to do is loop through all of our exclude modules, and then we're going to check in name. So we're going to see if this is in the name of any one, basically if any one of our exclude modules is inside the name that we're currently checking, and that's it. And all we're going to do is wrap this in any, so it's going to check if anything in this list is true. And so what this will end up doing is this. We can do print name, and then we can do self.exclude end name. And this should make it pretty clear. Remember, our only exclude module right now is the classifier. Looks like I made a quick mistake here. So it should be self.exclude. Oops. Exclude. There we go. So all the layers, notice that these are not exclude modules, so they're false, right? Because they're not exclude modules. But these four have the word classifier in it, so they are true because they are an exclude module. So let's go ahead and do that. So we can go ahead and do exclude module name check. That's fine. So we're going to do if it's not a exclude, so if it's not in one of our exclusion modules, right? So if it's not one of them, then we can go ahead and shut off gradients on that specific parameter. So we can do param.requireSgrad is false, right? So we're going to loop through all of the layers, check if this layer is in our exclude module. If it's not in the exclude module, then go ahead and shut off gradients on that layer, and we're good to go. We're also going to do so we have a exclude module name check here. We'll have another one here for target. So we can check, is this a target module or not, for the exact same reason. So we'll just call this TGT, and this should be target modules. So this one will check, is it an exclude module? This one will check, is it a target module? Other than that, exactly the same. So now that we have that set up, we can now disable gradients. Let's check that that works. Any bugs? Nope, looks like we're good. And just to verify, right, we can do a quick sanity check here. Let's just compute the number of trainable parameters, and we should see it go down. So let's do print, right? Because if we turn off all these gradients, then and let's print out what it was before, trainable parameters. So when we shut all of our gradients off, we go from about 124 million parameters down to about 592,000, which is coming from those last couple classification layers. So that means things are being shut down, so we're good to go. All right. So now that we have our gradients shut off, now we have to actually apply LoRA. So now is our time to apply LoRA. going to write a function called self.apply LoRA, and we're going to pass in self.LoRA model, right? That's the thing we want to apply to. And so you'll see why we're doing this, doing it this way in just a second. First of all, let's talk about how named children work in models. Actually, let's keep all of you. Just leave the LoRA model out. So we've seen named parameters before, but there's actually another thing called named children. And so the way you can think about it is these graphs are basically these models are basically like a tree that we can recurse through. And so the idea is we can do for name param in model.named children, and it's not param, it's for name module in model.named children. We can print out the name and print out the module. And so when we do that, you'll see basically this work out. We have so remember, the full RoBERTa model had the RoBERTa, which is the RoBERTa backbone, and then the classifier, which is just the classification head. So notice how it chunked it up, and then we can break it up again. So the next one we expect, the next kind of layer, is a RoBERTa model, is embeddings, which will be all the embedding stuff, and then the encoder, which will be all the encoder stuff. So let's check that. So we can do, let's loop through one of these modules. We can do for name, let's do name to module 2 in module.named parameters. And then we can print out name 2, print module 2. And let's just throw a break here so we don't go through both of them. But now you should see that, my bad, named children. That was muscle memory. So named children, and you should see now we have embeddings, which are the RoBERTa embeddings, and then the encoder, which is the RoBERTa encoder. So that's the key idea. That's the main idea here. We're basically taking our model, we're taking this module, and we're recursing through it, right? We're just going through every layer. So if we look at our full model, print model, we're basically going through it in terms of its depth, right? So if we look at the model, this full model, the things that are on the outermost layer is the RoBERTa, which is all of the RoBERTa model, and then the classifier. And then inside RoBERTa, we have what's on the next layer. We have embeddings, which is all the embeddings, and then the encoder, which is all of this stuff. And then if you go in another layer, the embeddings is really just, in this case, it would just go through all of these, right? Word embeddings is embedding, position embeddings, ... So that's the key idea, right? That's the key idea. We're basically just looping through the model one depth at a time, and that's the way we will be accessing everything. Basically, this allows us to do it recursively because I can loop through my modules, do something, and then pass in this module to that again to do it again, kind of recursively. So it'll make sense once we actually do it. So let's go ahead and start coding it, and it will hopefully make sense. So we first have our apply LoRA. That's the function we're going to be writing. So let's go ahead and write it. We're going to do def apply LoRA. It's going to be self, and it's going to take a module, right? It's going to take a module. And so what we're going to do is at the level of the current module, which right now is just the model, so we're at the highest level, and so we'll loop through this. Basically we'll have RoBERTa, which will be all of this stuff, and then classifier, which will be all of this stuff, right? So let's go ahead and do that. We can do for name child in module dot name children. So at this current depth, first of all, if we want to convert a layer to a LoRA layer, it has to be of our LoRA layer type. So it either has to be a linear layer, it has to be an embedding layer, or it has to be a conv2D layer, right? Those are my valid layers. And it also has to be one of our target modules, right? So we have to first check, is this layer a target module? And if it's a target module, is it one of our linear layers, convolution layers, or embedding layers? So our valid layers that we can convert LoRA to. In this case, the first one is just RoBERTa, right? RoBERTa is just our embeddings, like we saw here. So RoBERTa is just this embedding. So RoBERTa embeddings is not an embedding type. We have to keep recursing in. Word embeddings will be an embedding type. Position embeddings is also an embedding type, but word embeddings is the one that we're going to update. Similarly, as we continue to go through this tree and recurse more and more, once we get to attention, query is a linear layer. This is a valid thing to update. So again, we'll kind of see how this works out in a second. We're going to do for name, children, and named children. We're going to do if self dot, this is why we wrote this helper function, target module name check, name, right? So if this is a valid target module, right? So it's in our list of target modules, then we can do our sanity check. We're going to do if is instance, if this child is a linear layer. So if this is a linear layer, then we've met both conditions. It is both a target module and a linear layer, which means we can go ahead and change it to a new LoRA layer. So we're going to do new layer is equal to LoRALinear, and LoRALinear takes in all the stuff that we need. So we're going to do inFeatures is equal to child.inFeature. Remember, we're replacing, this child is currently a linear layer. If it's a linear layer, we want to make sure that the new LoRALinear layer is exactly the same as this original one. So we're going to make sure it's child.inFeatures. OutFeatures is equal to child.outFeatures. Bias is true if child.bias is not none, else it's false, right? Then we have a rank. It's going to be self.config.rank. So this will, the rest of the stuff will actually just come from our config file. So I can just copy it in. So the rest of this is just coming from a config file. So again, these are all the inputs to my LoRALinear layer. If you can remember, LoRALinear layer takes an inFeatures, outFeatures, bias, and then all this stuff. And then there'd be kworks, but I'm not going to care about that right now. I'm just going to keep this as simple as possible. So this is my new LoRALinear layer. And that's the main idea. Now that we have our LoRALinear layer, we need to take the existing linear layer and change it. So let's go ahead and print out here the child. Let's print out here the new layer, and let's print out the name as well, just so you can see everything. Yes, and actually let's also print out the current module that we're on. There we go. And what I'm going to do is raise an exception here, just so it stops at this. So because we don't want to recurse through everything, let's just recurse through, let's just recurse through some of it, right? Oh, my bad. There we go. So what we'll see here, oh, did I not apply self.apply LoRA? Did I miss something? Let's go ahead and check. Print module. Oh, actually, I don't think I'm applying. Oh no, I am doing that here. Okay, so here's the full module. Oh, it's probably because it's doing the... No, it didn't raise an exception either. Oh, of course, because we're not actually recursing yet. We should probably do that. So we're going to check. Remember, we actually haven't dug in. So all we've done is check, is RoBERTa a linear layer? No, it's not, right? We need to keep going inside. So let's write that real quick. We can do, and we'll come back and write all the other layers in just a second. We can check, are there any more children inside this module, right? So we can do if len list child.children greater than 0. So does this child have, or basically this, does this child that we're currently on have any more children for us to recurse into? So that's the first check, because we want to basically, right now, the child is this entire model, right? It's literally everything. So what we need to do is see, well, does this have anything more I can go into? Yeah, of course it does. It has the embeddings and the encoder that I can go into. So we're checking if this child currently has anything else I can go into that I can recurse into. So that's step one. If it's greater than 0, that means there are more children for us to recurse into. And not self.exclude module name check name. So we're verifying here that, hey, do I have more children to recurse into? And is this not a exclude module? Because once we're at the classifier, right? Once we hit classifier, we don't need to continue recursing into dense, dropout, and out. There's no need to, right? There's no need to, because we want to exclude everything inside the classifier. right? So this way we're just doing that sanity check. And if this is the case, if there's more and it's not in our exclusion modules, then we can do self dot, again, apply LoRA on this current child, right? So that's the key idea. Notice how we're calling the function in the function. That's what makes a recursion, right? So we are taking the current module, looping through all the current children of this module. We're going to start swapping stuff out if it meets the condition, and then once we finish swapping things, if there were anything to swap, we'll just kind of keep going, and then we're going to check, okay, I'm at this specific child right now of this module, but does this child have more children that I can recurse into? So I'm just doing a sanity check. Are there more children, and is it not a target module or an exclusion module? And as long as these things are true, then I can continue to recurse, basically reapply this function again on this specific child right here. And so now this should work. Should raise an exception. So raise an exception because I said that. But what we can see here is we have, so the first child here is a linear layer, which makes sense, right? Because childs are the module. So there we go. It's a linear layer. The new layer I want to create is a LoRa linear layer, which is the same. So the original linear layer is 768 in, 768 out. And the LoRa linear layer is 768 in, 768 out, right? So we've created the same thing. The name of this layer, it is a query layer. It's one of our queries in our attention computation. And then the module that this layer is inside is this one. So it's inside this RoBERTa SDPA self-attention. It is this query layer that we're looking at. So that's basically it, right? That's what we need. And so there's two steps that we still have to do. Number one, we need to copy the existing weights of this child, this linear layer, into our LoRa linear layer. So we can do new layer, dot, again, this is why we wrote that load pre-trained weights function earlier. Every LoRa layer has it because we need to be able to copy an existing state dictionary into our new LoRa layer, right? So that's what we're gonna do. And also the reason we didn't do it directly, like why not just use load state? Because we inherited and a linear, so load state dict is in here. It's because if we try to load state dict, we also have a LoRAA and LoRAB in here. It'll just keep throwing warnings. And all we need to do is copy for this specific weight and the bias if it exists. So that's why we're just copying for this weight and bias. So let's go ahead and do load pre-trained weights. And we're gonna load it from the child, right? This linear layer in this case, dot state dictionary. So that's our new layer. And then all we need to do is use the set adder, right? Set attribute. And set attribute lets me say for this module, right? In this module that I'm currently in, which is my RoBERTa SDPA self-attention, the thing that is called this specific name, and so in this RoBERTa self.sdpa attention, I have a thing called query, that's my name. I want to set it to our new layer. It's currently this linear layer. It's currently this linear layer, but I want to change it to this new LoRa linear. And there's a couple ways we could have done this, but set adder is the easiest way to do it. So there we go. So that has gone ahead and created our LoRa linear layer, loaded the pre-trained weights from our child, right? Loaded the pre-trained weights from the linear layer that we're inheriting from. And then we're just replacing in this module at that name, I want to use my new layer rather than the existing one. And then we just repeat this 3 times, right? For the 3, and if you had more layers, I'm sure there's a smarter way of doing this, but how many layers could you possibly come up with? Let's just copy these other ones in because there's nothing different. If it's a convolution, same thing. Define your convolution, load the new layer in, set adder. If it's an embedding, create the new layer, load the weights in, set adder. And then otherwise just keep recursing and we are done. This will now go ahead and recursively convert our entire model to a LoRa layer, to a LoRa model using all of, basically using our target modules as our checking case. So let's go ahead and print LoRa model. When we do this, you should see that we have the same model as before, but notice that our embeddings, oh, looks like I got something flipped. Looks like we're flipping things that are not our target embedding. So let's just check that real quick. Let's see here. If self.targetModule.nameCheck, looks like I have a bug somewhere. Yeah, so it looks like we're basically flipping the wrong ones. So for name, child, and module.nameChildren, target module, name check. Maybe I made a mistake in here. Target and name for target in self.config.target modules. No, that's correct. Then we do for, let's check our query key value real quick. So, okay, so the query key values happen correctly. Our dense is correct. It's just on these on the embedding layer, it's wrong. So we're doing elif is instance. Oh, did I get a, oh, the tabbing is wrong. So I need to tab everything in once. Sorry about that. Tab everything in. And there we go. That's why the linear was correct, but everything else was wrong. So, okay, good. So now we are always doing the check for is it a target module? Otherwise, this wouldn't work anyway. Okay, good. So let's go look now. So we see we have our word embeddings are converted to LoRA embeddings, but the position embeddings and stuff are left alone. Our encoder, we see our query keys and values are now LoRA linear layers rather than regular linear layers, and our denses have also been converted to LoRA linear layers. Our classifier is left alone. We never touched anything here. And so now here's the most important part. Let's go ahead and compute. So we've disabled all that. Let's just loop through it right here. We can do for name param in LoRA model.named parameters. Let's print out the param, or print out the name, and then param.requires grad. Right? This will be kind of our sanity check about everything. So we can see that LoRA model embeddings, word embeddings, so these original word embeddings are not trainable. LoRA and LoRAB are trainable. Our original query vector here in the first transformer layer is not trainable, but the LoRA, LoRAB, and currently the bias is trainable. So that's the next thing we have to handle, the biases. Also, notice our classifier, everything's trainable, right? Everything is true. So next up for us to deal with is just that toggle for the bias. So like I talked about up here in the LoRA config, we have our, like, which biases do we want to train? That's pretty simple. Let's just go ahead and toggle them as necessary. So we'll just write another, method right here, def toggle bias grad self. And we can do for name param and self.LoRA model.named parameters. We're just going to loop through everything. First of all, if we only want to do this as long as they're not in an exclusion module, right? Because we want to make sure that we're not updating or changing anything about a model or about layers that have been excluded. So we're going to do if not self.exclude module name check name. So as long as this layer, the name of this layer, is not inside our exclusion modules, then we can do if self.config.bias is none, right? So we want to train no biases, then we do param.requires grad is false, right? We're going to just turn off gradients. Elif self.config.bias, if we want to train all of them, right? If we're going to train all of them, then we do param.equal all of them. Then we do param.requires grad is true. Else, right, elif, and this is the last check, we're going to do if self.config.bias is LoRA only. So we only want to train biases on LoRA layers, which means we also have to check that this layer is indeed a target module, right? Something we converted to a LoRA layer. As long as this is true, then again, param.requires grad is true. So this will just loop through all the biases. Oh, actually, one more check. If bias in name, right? We will only do this, right, for the biases. So there we go. So as long as the bias is in the name, then we do the sanity check. If it's none, don't train it. If it's all, train it. If it's LoRA only, check that it's a LoRA layer and then set it to true if it's true. And so this will go ahead and toggle our bias grads. So let's go ahead and add that to our list. We can do self.toggle bias grad. And the last part is, now that we're done, what we're curious about is how many trainable parameters do we have left. So we're going to do LoRA trainable params. It's just going to be self dot, again, the same compute trainable parameters that we wrote earlier. And so this is how many parameters we started with. And this is how many parameters we're actually going to train. And so I'm just going to paste this little string in so we can take a look. Right, and I guess, oh, I totally named it wrong, so there we go. And we can quickly check. Hopefully I'm not printing. Am I printing stuff down here? I still am. We don't need any of this anymore. So this will go ahead and print out that, hey, we started with 125 million parameters, but now we're only training about 2.4 million parameters, which means we're only training about 1.9% of the parameters that we started with. And that's awesome, right? So we've greatly reduced the number of parameters that we're actively training, reducing our memory usage and all that sort of stuff. So this is almost done, but again, remember, this is a nn.module, right? So it's a model. So just like every model, we need a forward function. And this forward function is just a dumb forward function. It's just going to be def forward self. And the thing about this forward function is it's no different than the forward function of the LoRA model, right? It's basically whatever the original model's forward function was. I didn't change anything. All I changed is the layers, but we've already written forward functions for all of the different layers. So all we need to do is just pass data into the model exactly how we were doing it to begin with. And so as a catch-all, we can do inputs and kwargs. There we go, right? Whatever. So this will basically be our catch-all. We want to take our inputs and keywords, and then we can just do return self.LoRA model inputs kwargs, and we're done. That's our forward function. So again, this is basically take everything that comes into the forward function that we pass in and just pass all of that stuff into the LoRA model. And this is just a catch-all that will just pass all of the stuff from our forward method to the LoRA model's forward method. But other than that, there's nothing else going on. So this is basically it. That has gone ahead and done all of our LoRA conversion stuff. All that's left now is to write the function to save the model. And this is actually something, it's like, oh, what's so special about saving the model? There is a little bit of nuance here that you can keep in mind. The main thing is that when we are saving the model, you have two options. So let's go back to here, right? Remember, these weight matrices that we started with are frozen, which means after we're done training, they never changed. On the other hand, the A and B is trained, and maybe the biases as well, right? So just keep it in mind that way. And so if you have a model that's let's say, 10 billion parameters, right? Like one of the big LLM models, 10 billion parameters. That means the original weights of that model, you have about 10 billion of them. That means every time, let's say you're fine-tuning your model, every time you checkpoint your model, it's going to take like 20 or 30 or 40 gigabytes worth of hard drive space to save that checkpoint. And that adds up pretty quickly as you're training, right? It just eats up more hard drive space. So there's basically two options that are available to us. Either A, we can go ahead and merge the weights, right? Merge the weights here, create the W prime, and just save all the weights, which will take up a lot of hard drive space. But we can do that. We can merge the weights, and that's why we wrote the merge weights function. We can effectively just take, instead of having a model that has all this stuff going on, just merge everything together, create your W prime, and then save the model as is, and then use it just like how you always do it. Or we can not save W, just save A and B, or just save everything that's being trained in the model. Just save the trainable parameters. Because when we load our pre-trained model, and then we can then go ahead and just load the extra stuff right after the fact. So just saving these parameters doesn't take very much hard drive space. So this is really just a hard drive space thing. Also, saving checkpoints for really big models just takes some time, so it just speeds things up. So just save the weights that you're training, and everything that you're not training is going to be the same after training anyway. So just get them after the fact. And that's the big idea. So let's go ahead and write our save function. So what this will look like is just going to be def save model. And we're going to do path. Where do we want to save it? And then our flag, right? Do we want to merge weights? And by default, I'm going to set it to false. And so what we're going to do is if we are merging weights, I'm going to throw a pass in there for now. Else, right? If we're not merging weights, then we only want to save the weights that are not trainable, like the things that are actually being updated, because everything else will be the same anyway. So we can create a state dictionary. State dict is just going to be a dictionary of name param in, or name param for name param in self dot named parameters. Right, there we go. That's our model, right? We're just going to loop through all the if. Oh, am I missing something? Self. Oh, sorry. This should be a colon, right? It's a dictionary. So name param for name param and self.name parameters. So I'm looping through all of the name parameters of this model, and it's as simple as that. But we only want to save them if param.requires grad. So only for the parameters that have gradient information, right? They can compute gradients, so they're being updated. Do we want to save them? Now these params here, when we go to call the save model, they're sitting on the GPU, right? They're sitting, we're actively training them. So they're sitting on the GPU. So we're just gonna write a quick function here called def detach CPU. So this will just detach them from the computational graph and save them and copy them over to the CPU. So we're gonna return just our param, and we're gonna detach it off the graph and then just move it to the CPU. It's just a quick helper function. And then all of our parameters, as we grab them, we'll just detach them as well. So this will go ahead and create a state dictionary of all of our trainable parameters. So we can go ahead and print, for example, print, let's do for, we can do, let's see here. Oh. Okay, there we go. I am doing something totally dumb. I don't know why I'm doing it up here. That's on this layer. We need to do it on our, whoopsie daisy. It should be down here. My bad. There we go. Okay, good. So otherwise, same idea. So there we go. So we have our state dict. Let's print for k in state dict dot keys print k. And so let's see what that looks like. When we go to do save model, LoRA model dot save model, and we'll just give it some random path. It doesn't matter. Let's go ahead and take a look. So it'll print out and notice what it prints out. It's basically our LoRA LoRA B bias, LoRA LoRA B bias, LoRA LoRA B bias, and also our final classification head. So these are our weights, right? So it's really as simple as that. These are all of our weights for our model. Nothing too crazy. We're just saving only these LoRA weights. So there we go. That's option one. Otherwise, what if we want to merge weights? So now let's do our merge weights is true, right? So we actually want to merge weights. And so to do this, well, we actually need to, we need to merge the weights first, right? So this is why all the LoRA layers that we wrote a merge weights function. So we can loop through all the layers and go ahead and merge them, because we do need to merge them, right? But before we save them. So let's go ahead and first, for all the layers, let's just go ahead and merge them. So we're going to do self dot merge weights self dot LoRA model. So we need to do this. So let's write a method again that's going to do the weight merging for us. And it's going to look pretty similar to what we've done so far. Merge weights self. And this is going to take in a module, right? So a module. And we're just going to recursively, again, go through the whole model. And if it is one of our LoRA layers, then we can go ahead and do the merge. We're going to do for child, or for name child in module.named children, right? So we're going to loop through all of the children of the specific module. If it is an instance, if this child is a LoRA linear, or it's a LoRA embedding, or it's a LoRA what did I call it? LoRA conv 2D. So as long as it's one of these layers, then I can do first, remember, when we merge a layer, how did I define it? We merge a layer, create a brand new layer, and then copy the merged weights into the new layer, and then return that layer. So let's just grab it. There we go. So let's just grab it. So we can do our returned merged layer is just going to be our child dot, and we're just going to call the merge weights function, right? Method on it. So we're going to go ahead and merge our weights there. And then we can do set attr, right? We're going to set the attribute on this module, exactly the same as before. For this specific module, at this specific name, I want to replace it with a merged layer. So the difference here is earlier when we were doing it, right, these lines here, I was taking a pre-trained linear layer here and converting it to a LoRA layer and copying my weights in. Here, I'm taking a LoRA layer and converting it back to the original layer that it came from and just using the merged weights there. So that's basically the same idea. Else, and again, we can do that sanity check. If len list child.children, so are there more children that I can recurse into? If it's greater than 0, then I can do self.merge weights child, right? So that's my sanity check. And we are good to go. I don't actually know why I have an else here. Right, there we go. All right, so this will go ahead and merge weights. And so now, let's make sure this works first. So if we merge weights, it should run with, looks like there's an error for k and, oh, because I haven't made my state dict yet. So state dict, so our state dictionary now is going to be the same as before. It's going to be exactly the same as before, except we're going to do it for all parameters. So we're not going to do it for param.requireScribe. Now, here's one issue that we're about to have, and we'll kind of deal with it now. So we're going to do for name param and model.named parameters. Print out the name. I'm going to throw a print, just a line break here. And you'll see why we're doing this in a bit. When we are, again, the key idea here is that when we are using, if we just save the LoRA weights, right, like this, if we just, so we don't merge the weights, if we just save the LoRA weights, then for us to load our LoRA weights into our model when we actually want to use the model to inference it in the future, I need to first convert my model to, because remember, we need to convert our model to a LoRA model, because initially this model here does not have any LoRA LoRA B, it's just a regular RoBERTa. So I first have to convert it to a LoRA model, and then I can load my LoRA weights into it, just like that. But if we go ahead and merge all the weights, right? If we merge all the weights and then save the merged weights, then I can load my merged weights directly into my model. Right? I don't need to convert it to a LoRA model anymore because I've already gone ahead and merged them. So there's no more LoRA A, LoRA B in these weights. I can just go ahead and directly load to my model the state dictionary of the merged weights. So if we want to do that, there's one small caveat that we're about to see. I think it should print out. So let's go ahead and take a look and see if it does. Just notice the naming scheme. Our RoBERTa, so this is the original RoBERTa model, the one that we're working with. It has RoBERTa embeddings, RoBERTa embeddings, RoBERTa encoder, RoBERTa encoder, ... Right? So we have all of these layers here. Notice in our LoRA model, we have RoBERTa embeddings. It's this layer, RoBERTa embeddings, word embeddings, weight, is the same as this one, RoBERTa embeddings, word embedding, weight. But all of the keys of this dictionary is prepended with .LoRA model or LoRA model dot, right? So that's just because that's how we named our model. So if we want to save this checkpoint, right? And you'll see I have a bug about this later, so I just manually did it later, but I might as well fix it while we're doing it here. When we want to save a checkpoint with all of our weights, because we've already gone ahead and merged them, then we might as well just delete this. So we'll just delete the LoRA model dot from all of the names, so we can just directly load these keys into our existing model, and there won't be an issue. Because when we load weights, right, it's dependent on the name of the keys, and it's finicky. So we're just going to go ahead and do that right here. So we're going to have our name, except we're going to do name dot replace, and we're just going to replace LoRA model dot with just an empty string. So now when we run it, everything should be the same. So we have basically our RoBERTa, and then again, this is RoBERTa, right? So we have this, we don't have that extra LoRA model dot at the beginning, just so we can directly load things like our classifiers straight into our classifiers, right? So just a sanity check, but it's helpful to do. So now that we have our state dictionary, everything ready to go, we can finally use save file, which is from the safe tensors package. We can save the state dictionary to the path that we want to save it to, and we are officially done. This has now completed our RoBERTa or basically LoRA application, and I have examples on my GitHub fine-tuning both RoBERTa and a RoBERTa and vision transformer with this method. So let's go ahead and take a look at what fine-tuning these models look like. For this part, like I mentioned, I don't want to write any training scripts here because there's nothing fancy about this training script. So I'm just going to run existing ones, and then I'll just show you the results because that's what you care about anyway. So what we're going to do is look at this. Let's look at the train text classifier function. This should look very familiar, nothing new. Now, all I've done, this is just a very simple classification function, problem on the IMDb movie review dataset. So that should be familiar to you. I'm fine-tuning this specific model. And here's just basic training parameters. Here's all my LoRa stuff, right, that I want to train query. These are my target modules, my exclude modules, rank, that sort of stuff. And then basically the key part about this code is I have a couple of different options. I either train the whole model as is, or I train just the classifier head just to compare. And then I also use LoRA just so we can compare the different methods, right? So we'll be comparing kind of the two typical fine-tuning methods: fine-tune the whole model, fine-tune just the classification head, and then fine-tune the whole model with LoRA, right? LoRA applied. So nothing else changes. This is me doing it. We'll also talk about gradient checkpointing really quickly in just a bit, but just kind of ignore that for now. This training script is nothing fancy. It's just me looping through, training stuff, yada, yada, yada. And I have here just me saving my model. So first of all, if you don't know what accelerator.unwrap model is, I'm using distributed training here. So accelerator, or the Huggingface accelerate, puts a wrapper on top of the model. So model methods, like any method that you write, won't be directly accessible. So we need to unwrap the model, and then we can use the save model function. And I save it both with our full weights, right? So merged weights, and I save it without the merged weights, and we'll see what that looks like in a bit. Now that we have, so yeah, again, very simple training function. You can look at any one of my other videos or intro videos where we train a classifier, and it'll look just like that. So nothing crazy. Now let's just, I know this always slows the computer down a little bit, so hopefully it won't lag. I want to just compare our training real quick. And this is kind of the important part that I want to mention. So let's do accelerate launch. And before we do that, let's also open up a NV top just so we can see GPU utilization. Accelerate launch, we're going to do train text classifier .py. So here we go. So like I've been talking about, the whole purpose of LoRA is to give us really convenient things, especially to use less memory, right? Because we're training so many fewer parameters, we're hopefully using less memory. Well, let's take a look. Right now, we're using about 20 of my 48 gigabytes of GPU memory, right? So on each GPU, we're using about 20 of the 48. So, okay, that seems fine. What happens if we don't use LoRA? So let's do use LoRA as false. I'm going to use LoRA as false. What happens if we don't use LoRA? So we're comparing, so LoRA is using about this much memory. Now, how much does it use when we're not using LoRA? And, well, that looks about the same, right? Like, where's the memory savings? We spent all this effort here reducing the number of trainable parameters just so we could have this additional memory savings, but we're obviously not seeing it. And this is because LoRA by itself does not give you memory savings, because a lot of the memory that your GPU uses comes from not the parameters that you're training, but all the intermediate activations that the model has to solve. So, or has to store. So again, if you, we'll do a whole video on backpropagation later, but the idea is that for, if you have a linear layer right here, right, a linear layer, and then you have another linear layer, and then another linear layer, right? Because we typically stack linear layers together. And let's say you pass X in, and this will produce an A, which will go into the next thing, which will produce a B, which will go into the next thing, which will dot, 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 right? All your linear layers. So what goes on the GPU? The GPU has to store the weights of the linear layers, right? It needs to store the data, X, but that's only for forward propagation. For back propagation, we need to have these intermediate values available because we need to take the derivatives, right? And those derivatives involve these intermediate values. So we can't delete them. We have to keep them. And so the model stores both, basically our inputs, all the model weights, everything else, and it also stores these intermediate activations. And these intermediate activations is actually what takes up so much of your GPU memory. Later on, for example, when we train a latent diffusion model, we'll be training a model that's almost 1 billion parameters, but the latent space is basically the size of something like MNIST. And so training that model is no problem. Like, even though it's so many parameters, the size of those hidden activations, all the activations from all the intermediate layers in the model, is no problem. So our memory savings are not coming from LoRA directly, because even if we add LoRA and we add some additional like layers here, right, that go next to it, the LoRA layers, and then X goes here, and then A goes here, and then B goes here, we still have to store all of these intermediate activations. There's no way getting around it. And so we need to do something else. And the main technique here is something called gradient checkpointing. And I'm not going to go into too much detail about this. PyTorch has a really great article about it. But the idea is this. Basically, the thing is that when I go from linear, when I pass an X to linear and produce A, right, I need to keep A for the future back propagation I'll do. What if I just say X X is already sitting on memory, so I can just keep it there. So what if I produce A, and then after I give it to the linear layer, I go ahead and just delete it. I delete A, right? I delete A, and then I keep going, and then I delete B, and then I keep going, and I don't keep these things. During back propagation, right? During back propagation, PyTorch will automatically redo these forward functions to recompute A, redo this forward function to recompute B. And again, let me just pull up their PyTorch checkpoint. They have a great line that makes this very convenient to understand. So checkpointing is implemented by rerunning forward pass segments of each checkpointed segment. And the key idea is activation checkpointing is a technique that trades compute for memory. So we are having to redo some of these forward propagation computations, but that still allows us to train models, even if it takes longer, to train very large models because we don't have to store all these intermediate checkpoints. And maybe it doesn't seem like a big deal in RoBERTa because I'm able to easily train with my GPU memory that's accessible to me. But if you're training a model like Llama, or even bigger, like 10 billion parameters, 50 billion parameters, these really, really big language models, gradient checkpointing is basically your only hope of being able to do that within a reasonable compute budget, right? And so this is why, if we really want to see weight savings or memory savings in fine-tuning models, we have to use gradient checkpointing. Now, the really neat thing is in all of the Huggingface models, they have gradient checkpointing already built into them. So they've already gone ahead and put checkpointing where they think it's most optimal. In all my past implementations, haven't bothered putting in checkpointing, but that's something you would obviously want to do and wouldn't be very hard to do. Adding gradient checkpointing is just like an extra couple lines of code wherever you want to do it. So we're going to go ahead. We have added checkpointing to our model. So now let's see what the memory usage. So we can go ahead and run this. And again, we're more curious about the memory usage. Again, remember, the memory savings here are all coming from checkpointing. And we can see we're using about 8 gigabytes of memory now compared to the 20-ish that we were using before. So that's a sizable saving, right? I mean, we're training in BrainFloat 16. We're trying to do mixed precision training. We're trying to do our best to be as efficient as possible. And this is just one of those ways of doing it. So really the savings of LoRA only show up when we're doing stuff like this. And LoRA actually shines when you're training insanely big models, like 50, 60, 100 billion parameter models, like just really big models where you just don't have much of a choice. By the way, this is mostly just to give you a general idea. This should give you the background you need to go into things like QLoRA, which is a quantized version. I'm not going to talk about it too much right now. I have an example of QLoRA actually implemented on my GitHub. You have everything you need to understand that now. It's just instead of using regular linear layers, we're using quantized linear layers because, and to do that, we use bits and bytes. But again, I don't want to go too much into the weeds on other stuff right now. If y'all are interested in a video about QLoRA, I can make one later. But yeah, QLoRA and LoRA, 99% of the code that we wrote is literally identical. So I feel like me making a video would just me saying the exact same thing again. You're better off just going and taking a look at that. Look at the repo and it'll immediately make sense because again, the code's the same. So all we're really curious about now is what are the results like? So let's take a look, right? So again, just to give an idea, why does LoRA matter? None of this. We already talked about all this. Okay. So in our fine-tuning results, for the vision transformer, when I train all of the parameters on, so I train the vision transformer on the, what do you call it? The foods data set. So there's like 100 different types of foods, like hot dogs and whatever. And the model has to classify, like, what is it? So when I fine-tune my vision transformer on the foods data set, when we fine-tune with all the parameters, we get about 89% accuracy. When we fine-tune with LoRA, we get about 85% accuracy. Now, I didn't optimize or tune my rank or LoRA. I didn't do anything fancy. I just used it directly just to get an initial comparison. But we're training about 2% of the parameters of what we started with, which is awesome. But we can see that by doing LoRA here, we did have some drop in accuracy. It's not too bad. And maybe using a slightly higher rank or higher LoRA alpha would help with that, right? Again, that's the experimenting part where you try different hyperparameters, see what works well, that sort of stuff. When you just train the classification head, you get 77% accuracy. So we're seeing here, we're kind of in the middle ground, right? We're fine-tuning effectively the whole model at a reasonable compute budget, and we're getting better performance than just fine-tuning the classification head. And this is why LoRA is such a powerful tool, because we're using not too much compute, but we're getting reasonably good results. Again, for the RoBERTa model, for the IMDb classification, we get about 95% accuracy on training all the parameters, and about 94% accuracy when we train the parameters that I mentioned, right? And again, a massive drop to 82% when we switch to just training that fine-tuning head. So this is, again, really good to see that we're getting these gains here. We're getting like very similar performance without as much of a compute budget. Again, it's obviously best to be able to fine-tune the whole model as long as you have sufficient data. That's just typically not an option because I'm not Google with just buckets of GPUs lying around that I can just train on, right? So either way, and again, the memory savings are really coming from the gradient checkpointing. And that's just something to keep in mind. And I think gradient checkpointing is, if you go to use PEFT, for example, as far as I remember, gradient checkpointing is already on by default. Because if you're having to use a technique like LoRA to reduce your compute budget, then you're going to need something like gradient checkpointing anyway to continue reducing that compute budget, even at the extra cost of the training time. Either way, like I mentioned, this code is mostly for education. It does functionally work, but it hasn't been battle tested in the same way that PEFT is. So if you're going to actually use it, then go use PEFT. But let's call it here. If you have any questions, drop it in the comment section below. But I will see you in the next video.